was studying English. So Nour is my PhD student in France. Still have some students at Eurocom, which is a engineering school. This is one they call, let's say, France. So she comes with a bachelor degree from computer engineering from Telecom Paris of the good schools in France. Then a master in data science from Eurocom, and now a PhD actually in Sorbonne University, where they get it in English. Complicated things. And yeah, I'm going to present some recent works. It does other stuff as well on Omial, with some kind of theoretical tools from information geometry that we're trying to do for Bayesian Federated Learning.
Thank you very much for the presentation. Good morning, everyone. I would like to start by thanking all of you attending and the organizer of this talk. I cannot say that I'm stressed, to be honest. So let's say I would hope that I enjoyed Granada and Alhambra against the again, more plans. So I start first by thanking Giuseppe, who's another PhD student of Marius at Eurocom, and Boris. So Boris and Marius, who have involved with the work that I'm going to present today, and other stuff. So Marius is also not only about like talking about Bayesian Federated Learning, but also some Greek philosophy. And this Greek spirit, let's say, inspired me to start my presentation with the following story. So, human knowledge has always evolved by questioning our first explanations. Aristotle saw gravity as a natural tendency for the sun, and centuries later, Newton defined it as a universal force. But that wasn't the end of the story, actually. Einstein believed that gravity is the curvature of space-time itself. So today we are in a similar moment with AI. Models are powerful, but without explainability, we can't really understand, trust, or define them. Just like science, at least, we need interpretability to create trust in AI. At least for safety-critical domains like medical AI, here we have a model that claims that all is good with a very high confidence. But apparently it's not. And let's say we wouldn't be able to trust it again, even in case we remain alive and not like with the animations. Let's compare this with a reliable, well-calibrated model that we aim to achieve. The model communicates uncertainty appropriately, and even says, I don't know, and requires a human in the loop when needed. It cannot be the super powerful AI that knows everything, but it only actually builds trust and could save lives. Finally, trust cannot survive without privacy. Even the most explainable and calibrated model would fail us if it exposes our sensitive data. Without privacy, users are vulnerable, but with more privacy, AI remains trustworthy. And actually, our work connects these three key pillars of trustworthy AI: interpretability, reliability, and privacy. Reliability side, I would say we work with Bayesian deep learning, and for the privacy, federated learning is a good, let's say, gives better perspective than centralized learning. And for interpretability, which is the key contribution, is we employed information geometry tools. I started really fast with the general background on federated learning. So federated learning is a collaborative privacy-preserving machine learning framework that actually is built on the two phases. The learning phase, where we have models like clients that try to learn their own models on their own dataset without sharing the dataset to the server. What they do is that once they train their own model, they share the model to the server. There happens an aggregation. And So the global aggregation happens in the server, where it's just a simple arithmetic mean, and afterwards we send the global model to the client. It's an iterative process that ends with a global, like theoretically, let's say we would like a global model that generalizes well on all the local data without seeing the data. So we write it mainly in private. Federated learning inherits the uncertainty quantification challenges of deep learning, as we know. So uncertainty quantification, what it means is like basically we have this overconfidence issue in deep learning models. Sometimes we like very, very funny model, not that much critical, but we have this funny model that predicts ping pong balls as eggs, or on the opposite, eggs as ping pong balls. I wouldn't advise you to play ping pong with an egg, but anyway. The problem is that 99% confidence. So 99% confident that this egg is a ping pong ball. In medical, as I said, it's very critical. In finance and banking as well. Bayesian learning comes to mitigate this problem. So to incorporate uncertainty more naturally. And actually, I know that some of you have some fears from Bayesian learning, but what I would say is like it's very intuitive. It's how we actually human proceed basically. A newborn that can just like is like let's say 2 months and see the guitar. As I see the guitar, the only thing that has in his mind is prior belief about the guitar is just that it's wood that is bad, which is not completely wrong, nor true, but it's a prior belief. First experience in life, starts touching the guitar, and once starting touching the guitar, some sounds go back, and then he kind of updated his belief from the prior one, which was this is just wood, to this is wood that makes nice sounds. And afterwards, what we did is basically updating our prior belief, or the prior belief of the baby, with in life experience in machine learning. Keep experiment, looking into the data, which is experimenting the guitar, and to a posterior, which is now this guitar, we call it a guitar, but for him it's wood that makes nice sounds. And we do this a lot of times. Imagine again the same baby, then the mom comes and says, okay, this is not wood that makes a sound, but this is like, okay, wood that makes a sound, but it's called the guitar. So we update together the belief. And in machine learning, going back to technical stuff, in machine learning, this would mean basically we have a prior belief on the distribution of our models. So every parameter in our model, if you coded it, it would be not only a parameter, but all the distribution of possible parameters that we update using data to reach the posterior. And it's actually very effective to learn with using Bayesian learning from small datasets and to have a better uncertainty quantification. Mixing both, we have Bayesian Federated Learning. It's exactly the same framework. We have our clients, their data, they train their models on their data, and then just basically what we add is the posterior approximation. Since we work with variational inference or other, let's say, versions of it, not the standard one, where we need to approximate the posterior, and not with other methods like microcheck and the. Then we have these posteriors of the local models, but they send them to the server where happens an aggregation, just like in federated learning. And the question starts there. How are we going to aggregate these posteriors? Do you have any idea on how it's done in the literature, or how to aggregate posteriors in general, or distributions? Nicola? Okay. This is basically how it's done in the literature of Bayesian Federated Learning. We have basically two main methods. The first one, I would say, the weighted average of posterior statistics. Very simple. We have Gaussians or distributions with mean and variances. What we do is just like federated learning, but this time not only for the mean, which was before the model, now also for the standard deviation. So we have an average of mean and an average of standard deviations. Another way would be to do a multiplication of with posteriors. And this one I put it in red for a purpose. But I'm not gonna say anything. To just asking ourselves actually, the green one, what we call the weighted averaging of posterior statistics, even in the literature itself, it's called the naive aggregation, because we don't really understand what does it mean to do an aggregation of distribution statistics. Like, okay, we do the mean of means and mean of variances, but does this have an interpretation? What would the global model, like how would we justify our global model that is just an aggregation of means and standard deviations? For the red one, which is a multiplicative aggregation of posteriors, basically what we do is like, it's a geometric mean. So we take, they take the distributions, they multiply them, and the resulting distribution would be the global. What we propose is something more interpretable. We have this framework of barycenter. So what is a barycenter? I think the most simple example that I usually say would be in primary school, we have the triangle and we have the center mass point. That sometimes also we call the barycenter of the triangle. In that case, would be with some ways to third, to third, to third, and we have something in the center, right? It's exactly the same idea. You have some distributions. So now we are not working on the Euclidean space, but on the statistical manifold, so the space of distributions. And we want something that is actually somehow equally distant from all the other distributions. So somehow it's the average distribution. And this is the definition itself from barycenters in information geography. We have the n distribution, the n of the distributions. We select a divergence T, and just recap, what is a divergence? Divergence is like a distance. Mathematically, it's not, because it doesn't satisfy the three criteria of the distance. But it's how we measure, let's say, how far a distribution is from the other. So we select a divergence T, and the barycenter would be basically the distribution that minimizes the average discrepancy or the average divergence towards all the other distributions. So this framework is actually interpretable because in getting our global model as the barycenter of these distributions would basically mean that we know how to justify it given any divergence. So examples, if we take a Wasserstein distance as our divergence, we will reach Wasserstein barycenter. The good thing about Wasserstein here is that we have closed form solutions. So we don't use anything in terms of computational resources because we have like some assumptions on the Gaussian distribution that we use. Another barycenter would be the River scale barycenter. Just taking the River scale divergence, basically, we minimize the weighted sum of the divergences and we reach it. Another cool thing about this framework, it is unifying. Not only giving perspective to, let's say, giving the opportunity to get more ways of aggregating, but especially that we have this continuity between the deterministic regime and the Bayesian regime. Because if we take, for example, a Gaussian with certain variance, I think I imagine a Gaussian like this, and having a smaller variance, so we converge to a zero variance, basically, we convert the Gaussian would converge to a direct distribution. That moment, we are going from Bayesian learning to the deterministic learning. And Wasserstein barycenter or River scale barycenter, in the case of the variance conversion to zero, it's basically deterministic arithmetic aggregation. So how it's used in pedagogy and all the methods that are building on federated aggregation. Another thing would be the red method that I put in red, basically the multiplicative aggregation of posteriors. It's exactly the same as doing River scale barycenter. So basically, this is a bigger family of ways to do aggregations. And we had, like, one of them is basically already used in the literature without calling reverse barycenter. So without giving it the interpretability side. Just say, okay, technically speaking, we do multiplication of posteriors, and that's it. Third point in this slide would be that we actually had the convergence theorem. So assuming the d-dimensional Gaussian distribution with independent marginals and using either the reverse barycenter or Wasserstein barycenter, this framework inherits and preserves all the convergence properties of the dash for non-convex scenarios with both homogeneous and heterogeneous data. So here, what I would like, let's say, I will stop a bit here at the moment. What we have is a barycentric aggregation, which is a framework that gives interpretability, that gives unifying, like unification of methods, the Bayesian methods, as well as the deterministic ones, because there is this continuity between the two regimes. But then we know that in federated learning, people are not only interested actually in the global model itself, because there is always this issue of heterogeneous data, heterogeneous clients, and there we need some personalization. So, okay, we have local models, we have a global model. Our global model, in principle, should generalize better than the local models, but as a client myself, I wouldn't always need the global model because most probably it's going to be worse than my model on my local data. So the best thing would be to find something, I would say, in between the local model that wouldn't generalize that well and the global model that is not perfectly fitting my data. The question would be, how are we going to do personalization in this scenario? Again, information geometry. So what we propose is a framework that builds on information geometry projection, basically. And I hope until here is everything fine. Okay. But now it's not gonna get more complicated than that. It's like we have the local, what I put here PK, and I'm short. So what we put here PK is our local distribution. And this local distribution is basically what we had from the last iteration in our federated learning, in our Bayesian Federated Learning algorithm. And the global one would be PG there. So we have these two local distributions, the local one and the global one. We put, let's say, we consider a sphere centered in the local distribution with a certain radius. And we want to project the global distribution on top of it, onto the sphere. What we would have is what we call PGK, PGK1 or PGK2, depending on our radius, is the personalized distribution. So, of course, the radius here plays the role of controlling the level of personalization. If you can see the small sphere, the more red one, let's say, that one has a smaller radius, and so the distribution PGK1 would be closer to the local distribution than to the global one. The opposite thing compared to PGK2, which is closer to the global distribution than the local one. So basically, this is how we love to do personalization in the context of Bayesian Federated Learning, because again, it's very interpretable. We're doing the projection, mathematically speaking, this is very interpretable. Plus, we have this control parameter on radius, so we can control how much we want to personalize, and it depends on the client and not on the algorithm itself. So if the client says, okay, now actually I have the global model because the server sent me the global distribution, and locally I have my local distribution. Let's say the client is interested in a problem that is far from its data. It would use a personalized model closer to the global one or the global one itself. And if the client is interested in, let's say, I would say in some problems that are very related to their local data, which go to very small radius. But the projection, algorithmically speaking, and in the implementation is very costly, because basically how they approximate spheres with 1,000 or 10,000 points, every point is actually a parameter, and so on. The cool thing is that we have an equivalence, mathematical equivalence between the personalization and the aggregation, and the barycentric aggregation. So basically, this projection becomes just a barycenter between the two distributions, the local distribution and the global one. With certain weights, WG and WK. These weights, like the global weight and the local weight, basically, they are defined with a certain number. It doesn't came from nowhere. It came from the pool. And this lambda and the radius have an inverse proportionality, meaning that whenever the lambda is very small, we have a radius very big. So we have our personalized model is basically the global one. And the opposite, when the lambda is very big, we have a radius very small, and so our personalized one coincides with the local one. So just by selecting lambda in the weights of the barycenter, we are implicitly determining the personalization radius. We almost stopped with the, let's say, finishing with the theory, going into the experimental setting. We are doing Bayesian deep learning, but I would guess that most of you have heard how Bayesian learning is very expensive, in the sense like if you want to compute, usually using variation inference, if you want to do a simple method that needs at least times 3 or times 4 computational resources, and of course, the more you scale, the worse it is. The good thing is that we are using a method that is at the same cost of deterministic methods. So we are doing variation learning, we are gaining the uncertainty quantification, but with a cost exactly equal to federation. So the personalization step is cost-free, and the local training itself is exactly as if you are dealing with Adam or Aaron's program. And this algorithm is called Improved Variational Online Newton, so it's a second order optimization algorithm, and it acts in a very similar way to Adam. So in Adam, we have a gradient, right? So we compute the gradient of our parameter, of our loss, and in same, just like we sample from the distribution that we are learning, and we sample from that distribution, and that sample acts like our model, and we do very similar things to Adam, as you can see. The references are here. This is the, let's say, the paper that builds all the theory. It's a JMLR one, and then the icon itself was in the latter paper in ICN. For federated learning, we are simulating statistical heterogeneity among 10 clients with digital distributions. So just quick intuition is like, imagine we have 10 classes, 10 clients. Every client has this distribution. So all the clients don't have the same distribution, basically. This is how we do things. Empirical results. But before starting showing a lot of plots, I want just to have a small recap. What we did basically is like we have a barycentric framework to do global aggregation, and then after that we do the personalization via the information geometric projection, which actually is the same as doing a latest barycenter between the last global distribution and local distribution. We will do the experiments in the setting of heterogeneous federated learning with the Bayesian deep learning course. First thing is, do these barycenters actually, like, first question, do these barycenters make us lose in any performance metrics like accuracy or expected calibration error, negative likelihood for calibration and uncertainty quantification, the question is not. Actually, we have no statistical difference between any of the used methods for aggregation, like the empirical arithmetic aggregation, what I also call the naive one, or reverse case barycenter, best system barycenter, and others. But here I just chose to show this plot. But we also, so we don't lose in performance, we don't lose in cost because we have closed form solutions for these barycenters, but we need interpretability, as I said. Second thing would be to check the personalization itself. So for personalization, I mentioned the parametric lambda, the lambda that is controlling how much I go into the personalized version, into the local version, or into the global version. Here in the plot, I would just let you focus on this, let's say, for accuracy. So if we are in lambda equals 0, we are in the case of the global model itself. So we are not doing any personalization or localization, let's say. So the global model is achieving a certain accuracy, let's say around 65 for the CIFAR10 dataset. And every time we increase lambda, we are going into, this is in average, sorry, I didn't mention that, but this is in average over all the datasets. So whenever we increase the lambda, we are going to have a better accuracy on the local data, the blue line, which makes sense because now we are considering every client checking its own data, but we are considering the version that is closer to the local. The local would be what I put here, lambda equal infinite. So we have, let's say, for lambda equal 1, which is half the road between the global model and the local model, so the global distribution and the local distribution. We have almost the same results as the local one for the local data, but we are losing a lot in the global data. So that means basically, whenever we use the local model, we are losing in generalization, but we are not winning that much compared to a personalized version that is half the way between the global and the local model. So what would be cool is to use something in between, like lambda equal 1 or even 0.5, and not use the local model if you are focusing on even a problem that is very similar to your original data. The same applies for the two other metrics, the expected calibration error and the negative likelihood, which are the metrics that we mainly use to assess model calibration and uncertainty quantification. I think almost last slide for results. Like this, okay. The proposed one is the star. So the projection here with lambda equal 1 and Wasserstein barycenters for both global aggregation and personalization. And the other methods, VETPO, perfect BAM, perfect BANS are like methods from the literature. So one ICML, one CVPR, and one FRIPS. And we compare against these methods for 3 datasets. So every time the caliber needs the dataset and the shape needs the method. We show that actually for the accuracy on global data, local data, the best region would be top right. No, top left. Top left. And for expected calibration error and negative log likelihood would be what's correct. And we see that looking at this plot, our method resides almost in the best region at every time compared to other methods. So we are giving, let's say, we are having a method that gives a good balance across all metrics and datasets between the performance on the local data and on the local data. It wasn't the last slide on results, but this one is more like opening, let's say, because fairness is very big topic, and usually people don't focus just on client level fairness, meaning like the egalitarian version or the utilitarian version, which focus on the mean accuracy or worst case scenario accuracy, but also other metrics like demographic parity and so on. But just focusing on the client level fairness, we show that actually we have very comparable results in terms of these fairness to the state of the art. And what we also do here is basically in Bayesian Federated Learning, as far as I know, we didn't see a paper that looks into fairness, even from the client level perspective. While in federated learning, usually there is a lot of papers focusing on that. So this is like a first step toward also analyzing fairness in the context of Bayesian Federated Learning. I would say we finished this federated learning at the moment, and but we are not going that far from information geometry and Bayesian learning. So just we switch from federated to LLMs. Why would like to do merging of foundation models? I mean, it's exactly the same intuition compared to what we were doing in federated learning. At the end, apart from playing with massive architectures, the concepts remain the same. But why, like big companies or big tech and even academia looks into merging of foundation models, usually to mitigate a bit the problem of catastrophic forgetting in the context of continual learning. Because every time we just do fine-tuning on a new task, like we lose a lot on the previous one, so on the low, let's say, training or pre-training. And model merging seems to be a quite nice solution for that, at least to preserve the memory in terms of all tasks and units. But I love Bayesian learning, so we stay here and the variation of foundational models. You would tell me, okay, already foundation models are huge, and training them is not for everyone. And if we go Bayesian, that should be even worse, which is no longer the case, because the same. I mean, the paper that proposes IAFER also they tried training GPT-2 on it and ResNet 50 on ImageNet, and things are going well. So the same cost and the same time as training with IAFER with a better calibration, as it's a Bayesian method, and even better results. If you can see here, after 24 hours, like the red line, which is IAFER, is outperforming training with IAFER. Not only for training, also fine-tuning with learn. On Llama 2, 7 billion parameters here, this one is a bit newer, has a paper. So you can see that IAFER actually improves the LoRa fine-tuning, increasing accuracy by 2.8% and the expected calibration error by 4.6. Sorry, for the calibration error, it's not this low, but the results are from the paper. And for this note, it's mainly focused on the time, because again, there is this big idea that every time we go Bayesian, we use a lot on computation resources and on time, of course, which is no longer true using this algorithm. So here we see that using IAFER, you get even better results on common sense reasoning benchmarks for fine-tuning Llama 2, and with a similar time. So we don't use, again, in computational resources. Our beautiful projection plot. We do just an interpretation of the frame from the federated learning to emerging foundation models. So here we reinterpret what we called before in federated learning a global posterior to just the pre-trained foundation model posterior. And the local posterior, which was our local model in the federated learning context, to just the fine-tuned foundation model posterior. Once we have these two, we just, let's say, fine-tune with IAFER, you get these posteriors. You do the projection to have specialization, or equivalently, we are doing barycenters, right? So we can just do it between the background, the pre-trained model, and the fine-tuned one, or even between different fine-tuned models, because also this is apparently very effective in the merging foundation models literature. What we have emerging, like in the literature of emerging foundation models, very known mixture of expert, product of expert, Fisher version as well. But these are the same, like coming from the bigger family of D barycenters. So if we select the D to be the forward scale divergence, that means we are doing forward scale barycenter. But just here I need to, let's say, precise something. The forward scale barycenter and the mixture of experts are not the same thing. Just like forward scale barycenter is the barycenter in the parameter space. But the mixture of experts regards the predicted distribution. But having the forward scale barycenter as your posterior distribution, you just need to marginalize to reach the predicted distribution. And there you get the mixture of experts. So basically, these are equivalent, not exactly the same, but they are equivalent. Ensemble is doing somehow mixture of experts, but with equal weights. So it's the same as doing, again, forward scale barycenter, just the weight would be the same for everyone. If we look into product of experts, that one is exactly the same as doing reverse scale barycenter. Because product of experts is basically you multiply the distributions. And this is the reverse scale barycenter, which also coincides with the Fisher merging when we use exponential families, like and the cool, I would say the best thing of this story would be that this opens the door to other ways of doing aggregation. Not just stay focused on just doing mixture of vectors or product of experts, but try out divergences. Divergences is a big family. You can play with the parameters. You get another divergence for one goal, and for another one for another goal, and so on. At least for Bassi-Stein distances and another set of divergences, they are pretty much studied in the optimal transport literature. And I would say they are also showing great performance in terms of auto distribution, detection, and studies in general. So maybe if we go more into Bassi-Stein barycenters, we could maybe solve a lot of issues regarding the auto distribution problems that we actually have a lot in machine learning. Some limitations of this work. Like we were mentioning a lot of aggregation schemes. That's true. It's not that we are generalizing, we are unifying, giving interpretation, and so on. But the guy from Gemini team in DeepMind or in Google would tell me, oh, but my specialized model is small compared to the backbone. How are you going to do aggregation in this case? Which is right. That is a limitation because all this theory assumes that you have architecturally aligned models. So the big one, the global modeling, federated learning, or the pre-trained modeling foundation models would be as big and also the same architecture as the local model or the fine-tuned one. It's true that this is not a limitation just for this method again. This is what is done in the literature. But the cool thing is that even looking into information geometry again, we could solve this. So there is the Gromov Bassi-Stein optimal transport that can relate this assumption by mapping between spaces of different dimensionalities. But if we want to go even for an option that is more easy, more practical, more computer science oriented, would be just to do node distillation, and the problem would be solved. So it's not like, okay, this can only work for architecturally aligned models. In theory, yes. But then if you do node distillation, then it should also work for other problems. Yeah. I hope I didn't exceed the time, but we reached the very easy slides. Conclusion. So again, barycentric merging gave us an interpretable framework with controlling weight. So we can choose whether we go very domain specific or global knowledge, so generalization or very local. It's also unified merging schemes, either in the both in the Bayesian Federated Learning literature and also in the foundation model merging literature. And the good thing is that we have closed form solutions when working with variational families like Gaussians, which means we do all of this with zero cost. Closed form solutions are really nice, thanks to the math people. And the projection scheme, again, it's equivalent to the barycenters, cost-free, tunable. Maybe I didn't focus much on that point, but it also gives a lot of freedom to the user, to the client, to choose, which is not the case in other methods for federated learning. Usually, the algorithm itself delivers the personalized version. So it's not really up to the client to decide to which extent we want to personalize. Future work, before that, the state-of-the-art results, very coming in the machine learning community. Yes, we achieve also state-of-the-art success. I would say, for me, it's not the most important part in the presentation. Future work, very simple, very short. Federated learning is nice, but not as formal as differential privacy if you want to ensure privacy. So the cool thing would be to integrate also differential privacy. And this is an ongoing work, actually. Yeah, I think, thank you all, and I'm happy to hear your questions.
Okay, thank you very much. If anyone have any question?
I think this is on the learning, more in adversarial attack on events.
Nice.
We can talk wherever you want.
Sure, I would love to.
Yes. I have some questions also.
Okay.
I was wondering during your talk about what kind of distribution you're using for the prior distributions. I'm assuming that you're using Gaussians.
Yes.
Do you think that's enough to approximate all the clients, most clients as server file distribution, or have you find some scenarios in which maybe you want to use another kind of distribution? And if you have a situation in which you have several clients and one of them follows a Gaussian and another kind of distribution, can you mix it in the server using your approach?
Okay, let's start one by one.
Yes.
Okay. First thing, I will go back to this slide to make this, I think, easier. Yes, I will go to this one. So yes, we actually assume that all the clients are Gaussians, like are approximating Gaussians. With a mean and the covariance matrix that is like diagonal, which is the very common assumption in the literature of Bayesian deep learning. Now, back to your question, if we have clients that want to use different distributions, in theory it's possible. Practically speaking, I wouldn't say so, because like the first paper that I mentioned, which is actually this one, I wasn't even using Icon. I was coding things like in the standard variational inference way, and there you specify your prior in a very clear way and everything. But to be honest, which is a big limitation in the Bayesian deep learning community, I think, because most of them come from statistics and not from computer science background. We lack a lot of libraries. So already coding this for common priors, common distributions, let's say, it's not the easiest task. But then if you also want to mix things, what you would lose basically is the closed form solutions in the barycenter. It's not like, I'm not saying theoretically it's not possible, it is, but whatever thing that you gain in computation resources and cost, that you lose it, because you don't have actual closed form solutions of example, Basses and barycenter of different kind of distribution. So that would be the first point. The second one, if I'm not wrong, if you can actually remind me, please.
No, I was thinking that I think you answered my questions in the same.
All of them.
Yeah, I think it was,
Okay.
it was like.
Then I'm happy.
But also talking about the solution. I think that when you use divergence, you have to make I think that in the case of the barycenter, I mentioned a theorem that said that independent of the divergence that you use, it's gonna converge, right? Or something like that. That it doesn't depend if you're using that one, okay. Because I want to say, do you have any intuition or something behind that? When should I use each divergence, or it's the same in every basis? Because, for example, for the part of the foundation models,
Yes.
you did this that I really like. That if you're using this divergence, you're going to reach of expert. Do you have this?
It's exactly the same. Actually, it's exactly the same. But why I'm not mentioning here, for example, forward-scale barycenter? Because here I'm focusing on Basses and barycenter, reverse-scale barycenter. It's just because in like mathematically speaking, if you want to do the forward-scale barycenter of Gaussians, it's not a Gaussian. If we want to project what we get, like the real forward-scale barycenter, into the Gaussian space, which we could do, and it also exists in the literature, the problem would be that this result, that I would call it Gaussian forward-scale barycenter, not exactly the forward-scale barycenter, that one doesn't preserve the assumption, or let's say I would call it also an assumption, the assumption of independent distribution, so the diagonal covariance basically. Why? Because I don't know if I can show you this, but maybe later. I'm not sure that I'm going to find it exactly where, but it's in the paper. Yeah, it's in the TMLR paper, so the second one. In the appendix there, you can see that the forward-scale barycenter, even to project one in the Gaussians, don't preserve Gaussian, as it's projected, but don't preserve the independence of parameters, meaning that it's not practical. This is not practical because if you code things, there you would need, basically, whenever you lose the independence, the cost, even in federated learning, going from federated learning to Bayesian, you multiply the cost, the communication cost by 2, because you are sending the mean, which was before the model, and the standard deviation vectors, the covariance matrix. Good thing that when it's diagonal, we multiply this communication cost just by 2. But when we lose this diagonal thing, there you will lose a lot in communication. And this is why we don't use forward-scale barycenter in the federated learning context. But for foundation models, as you mentioned, it's exactly the same as doing the mixture of experts. But these do it directly on the predicted distribution. So you are not sending the posteriors or the matrix of the distribution. So that's the main difference. Whether to choose between reverse scale or Basses time, I would say Basses time. This is very personal opinion. This is not science. That's why I want. Basses time gives more, let's say, continuity, because it's doing optimal transport. If you transport a mass from sand, like a mass of sand, to a hole, there it's very continuous in the way you do it. Reverse scale barycenter is not that beautiful, but then it depends on the application, of course.
I think about more comments, but just one final. I don't know if anyone wants to ask or they want to go so much. I was thinking all the time that the differential paralysis is going to be a problem.
Yes.
And you said that also in the conclusion. I'm not sure about that, but don't you think that you are going to break all the Bayesian learning at the differential paralysis? No?
That I cannot answer, no.
Okay.
Because I'm working actually on that. And I would say it's not an easy problem, but the main issue would be how to assess the noise. Because doing variation learning, you already have noise. And then adding the noise of differential privacy, you have another noise. So the problem is not breaking variation learning while doing differential privacy. The main problem would be how to assess or how to compare in a fair way a differential private variational method to a differential private deterministic method. So the problem is in the evaluation and not in the method itself.
Okay.
So I think there is a space of very nice theoretical contributions.
Yes, because I think it's the main concern about using variation learning.
That is a very nice question. Thank you.
Thank you for your.
Okay, I have two questions online. One is Natalia. I don't know if can speak.
Yes, hello. Thank you for the talk. I was wondering from the side of continual learning that you mentioned it is a way to perform model merging. And I was wondering two aspects, like is there any advantage by your proposed approach for this model merging that maybe collapse less as more models are merged into a joint model? Or I don't know if you have any experience on this or any positive side of doing this approach. And also the other side of interpretability that you mentioned, and that I see is more mathematically, but from the end user point of view, how can we maybe explain more the merging of knowledge in a continual learning sense for the end user? Thank you.
Thank you. I'm going to try to reformulate the question just to be sure that I understood it correctly. And please correct me if I'm wrong. So the first question was, do we have some computational issues once choosing to do these approaches of merging, right?
I mean, for model merging and accumulation of model, like task arithmetic, I don't know if you are familiar, like when we merge models and we want to perhaps erase some knowledge, or instead of training from scratch, we maybe add several models, weights, and so in the sense of model merging and task arithmetic, what are the advantages of using your approach?
Okay. I would say if you are doing this with some foundation models or even smaller models, there is no difference, because what I was trying to say is like the methods that are used now are just coming from the theoretical family, so the family that is called the barycenters. So whatever you are used to use at the moment, like for example, mixture of experts, then you are acting on the legit distributions. But if you are doing product of experts, then you are acting on the parameter space, somehow multiplying the models. So the difference between our approach and this approach is that if you choose a divergence that is forward KL or it's reverse KL, there is no difference because they are exactly the same. If you use other divergences, so then you get other merging way, for example, Wasserstein, I would advise using it, like the Wasserstein barycenter, because again, it has nice properties on the outer distributions. You mentioned task merging, so I would assume you maybe, please correct me if I'm wrong, but you use like models that are not learning the same task. So maybe one is doing, I don't know, classification or something on speech, the other will be on images, and so on. There, again, you can do this just by doing some distillation or just by leaving out the last layer, so the fully connected layer that got the decision, and all the rest, like the proposed method. Again, there isn't, the game would be in interpretation. I'm going to answer the second question on explainability, but the game would be in interpretation, not losing cost and just saying, look, people, there is this family that is exactly what you are doing, but maybe offers you other alternatives as well to check. For the explainability part, so that's true that the method focuses a lot on the interpretability by design. This is why I call it interpretability. I'm not at all expert in explainability, but as far as I understood, is that if you go explainable by design, then people in the literature will follow more interpretability. When we are not doing explainability post-hoc, so we are not explaining the output of why this model outputted that decision for the specific input. This is not a post-hoc explainability problem, but it's in the design itself. So if you work like for finance or like in banks or in hospitals, they care about why this global model, why this way of doing the aggregation. So it's more like, okay, we have this foundation that means that we are equally distant to the others. Well, it's not the case if you just do a weighted sum of means and a weighted sum of standard deviations. So the explainability comes there, that we can justify our global model decisions because it's the global model that is actually in the center, really, of the local ones. So this would be my answer to the interpretability point.
Okay, thank you.
Okay, I have more questions here. And one is it's about Mario. He has writing. He said that usually divergence terms are not symmetric, like the key A,
Yes.
and he's asking if the order is very relevant.
Yes. And if I may ask, what is the question?
And the question is the order of the term relevant?
Yes.
Maybe it's just a detail.
They are. Actually, then it comes out to the definition itself. It's here. So the order that we use in this one for the KL. So KL is non-symmetric. Reverse KL is the opposite way of doing it for KL. But Wasserstein, for example, it's symmetric. It's equal distance. So you don't have this issue of ordering. But then you just, if you put your G here to be KL, it will be PK cube. If you put the reverse KL, it will be cube PK. But then you just should be aware of the order you choose, and you continue all of the work with the same order so that you don't split, like you don't mix KL and the reverse KL in the coding and everything. But then, yeah, of course.
Okay, thank you. Any question? Yeah.
I'm also doing like a personalized federated learning. I have questions like on your experiment, like how many you did like for the personalization?
You mean this one?
Yes.
Okay. So here we can, like, we are using mainly three data sets: fashion and NIST, SVH, and sector plan. And we split, like, let's say the training data of fashion and NIST, we split it among the 10 clients. And we use Dirichlet distribution to do the split. So Dirichlet distribution is a parameter, which is called beta in general. There we put beta equals 0.5. And this gives something similar to here, meaning that our client 0 has, let's say, less than 500 samples with class 1, but will have almost 2,500 samples class 5, while client 7 has like more than 3,500 samples for class 9 and almost 0 samples of class 4, and so on. So it's not like we are putting every client has only 1 or 2 kind of classes, but it's like a distribution, it's more random, and we simulate this like that. We are not the only ones doing this. It's like very common use of the research to do it.
And also when you do the experiment, like every client share the same the structure of the model, right?
Mm-hmm.
And do you meet like some issue, like permutation issue, because your projection is on the like parameter network, and if the client has a super noisy and a very like different like distribution of the data, and probably the model, like even the same position of the neural, they learn the different things. So no matter how you combine every parameters together, but it doesn't work. It couldn't find out like optimal position of optimal parameters for them. Because this is my opinion. Like I want you to ask me, like I want you to explain this to me, because before I'm also doing like parameters level like combination, but I quit. I found like permutation invariance is a problem. I can't like solve this way to fix this problem.
Okay.
Yeah, that's why I'm working on distillation now.
Nice. I mean, nice choice to work on distillation. That's aside, but for the aggregation, when I think, I mean, please correct me if I didn't get your point. Go to the very first slide, because we are mentioning federated learning in general, not even Bayesian. So you are mentioning disaggregation. So there is the weight, right? I'm not mentioning the parameters of the model themselves, but the weight of the aggregation, what we call the omega k. There is very different ways of doing that. The way that we are doing is basically to assess the importance of the model with the amount of data it has. So if this client participates with, I don't know, 10K samples, and in total they have 60K samples, but they have 10 clients for sure, that model will shift more the global model to its local one. But then, again, this is a very common way of doing it. But then the choice of the weighting is a very nice question. And I didn't mention it in the slides, but if you go Bayesian, there you can even use, actually here, no, not here. Yes, you can even use the weights that come from the uncertainty, because once you go Bayesian, you have some models that have very high uncertainty, others that are more certain. So there's some deviation is a bit smaller. There you can give more weight to the client that is more certain. So probably its local optimization was better than the other one, than to the model that has higher uncertainty. So this is also an advantage of going Bayesian. This how to choose in case we have strong heterogeneity. So we can look into the uncertainty of the models, which wasn't possible if you work with deterministic, in the deterministic scenario.
Yeah, because my problem is like even two models, they share the same architecture.
Yes.
But for example, the same position, and they have a different meaning of different function, and you just like projection this one to the same position in another model, right? The projection is like this one. The projection is like these parameters project to another one, but it's in the same position or
no? Yes, in the same position, of course, but not the parameters. We are projecting distributions. That's the difference. Yeah. So we are not projecting parameters, but distributions. So we are projecting onto a sphere. So it's not about taking a parameter, let's say 0.5, and sending it to 0.1.
Yeah.
This is not what we are doing. It's more like, okay, we take a distribution of our parameters, and then we project it onto a sphere that is centered in another distribution, And so you get another distribution. You don't just get a scalar. And that's the difference. So, and of course, as you said, position by position, in the sense like, if you mention a parameter, I mention a distribution on that parameter. So we do the projection aligned in an aligned way. So I'm not projecting the last layer onto the first layer. I'm having the last layer here, the last layer there. I have my distribution on the last layer here, my distribution on the last layer there. I project this one on the other.
But you still like presuppose like two different distributions have some like correlation. I mean, if even the same position, the neurons probably different meaning, like different function, probably they don't have relation even in the distribution of the parameters.
I'm not sure that I got exactly your point, but you mean in the task, like the task is different, or you?
I mean the same task.
The same task, the same
task.
architecture, and the like similar training, right?
Yeah. Probably because of the data distribution is different.
Yes.
So when they train locally,
Yes.
the different neurons learn different function.
Yes.
Like, for example, like this neuron
Yes.
only focus on
That's the main goal of doing the projection or doing the aggregation in general. The goal is to find something in between. So something that would generalize well for both scenarios.
Okay.
Because if, as you said, they are very different data sets or data distributions, you would have the local one, or you call it 1 or 2 or model 3. That model would be very local to the data, and if a new data comes for testing or for inference, if you are using the model for a real purpose, not just learning, would be you would need more generalization, and this is why you look onto other models, and this is why you want to learn from other models, and this is why you want to go closer to the others. That's the main, but it doesn't mean that you will lose completely on your local data. This is what I was showing here, actually. That's true. Here we have data heterogeneity between clients. It's true that the more you go local, so here it's like this is the average result of the local models. So the more you stay local, you will have bad generalization, but very good local performance. What I mentioned in this slide was basically why to go really local, as you are not winning in the local performance after a certain part. So if you stay somewhere in the middle, here for example, you have almost the same good local performance, but with more generalization. And this is the purpose of doing something in between. This is the purpose of doing aggregation or projection. Projection is more intuitive, but mathematically speaking, they are equivalent.
Okay.
I hope I answered your question.
Yeah, that's why I asked is like how 9D your distribution of the data.
I mean, with beta equal 0.5 in the Dirichlet, it's quite.
You try like use like a small amount of the data, not like 1,000 or 2,000. This kind of stuff.
I think the training, if I'm not wrong, in total is 60,000. So it's if I'm not wrong, it's 10,000 per client. But we didn't test with different sizes. It's more like because shifting can be very different. It can be like in the future, covariate shift, label shift, quantity shift, and all of that. We focus mainly on the label shift. Okay. So it's like the P of Y, so P of the labels is different.
Yeah, I'm also focused on the label shift. Yeah, we can talk later.
Sure.
Thank you.
Thank you.
Any other question? I have a question. It's relative with that previous question. Is when you say that there is you can personalize very lot the projection, changing the specific parameter, the lambda, and change the ratio. But the thing is, when you have a situation in which, imagine a real situation in which we want to learn from health information of different hospitals. Maybe there are several hospitals that have several similar illness, and there are other specific hospitals that there are more particular illness, for example, a special region in Africa or in America, but it's important because they could give information of different illness. When you say there is a specific, because the behavior of the different client can be very different, there are a specific automatic way to tune the ratio to say which could be more useful, because in your experiment, I think it's more or less random, or not, the client behavior, or the client behavior is more or less similar. But when you have different client with a very different behavior, you can, I don't know, or guideline or automatic tuning, automatic way of personalize or something. That's my question.
I would answer with two answers.
Okay.
The first one is that's true, especially in practical world, like as you mentioned, the healthcare, like hospitals and everything. Usually it's specialized either for like different illnesses that can show up in some countries, not others, or even by gender or by age and so on. This is why fairness is very important as a question for federated learning as well. But we can go from federated learning to hierarchical federated learning and clustering. And there it would be exactly the same what it's done on the deterministic federated learning literature, which is very huge and I think very rich for this question especially. And there is a lot of methods, even some that are doing game theory to solve this issue or this situation. But the most classical one is clustering. So you cluster the hospitals, like you put the hospitals in clusters, you just by looking into the model that they are sending, how they shift, and then you can understand somehow the data, and this is why differential practice is important. But yeah, the way like the models are shifting, you can get that these models, like these clients are more aligned together, and then you put them in clusters. And then of course, whatever thing you did in federated learning or Bayesian federated learning, you can do it for the small cluster, and then you do the aggregation between clusters. So it becomes more hierarchical.
Yeah.
That was the first point. The second one, now that I forgot, at the end you mentioned, yes, you mentioned automation of the projection somehow, like the choice of the lambda. How to make it more automated. Actually, this could be a nice extension of the work, because here we give full freedom to the client to choose its lambda. So to go very global or very local. But then you can even do some learning to decide what is the best appropriate lambda, and then you can maybe, I mean, for sure there is a space for work there, but you can even see do some more analysis on the data distributions there, not on the model distributions, because you could compare your local distribution to the new one that is coming to decide to which extent you localize or you go global. Because if the new data coming in inference is very different from yours, it would be smarter to go more global, because it's so more data. Implicitly. But yeah, I mean, there is space of turning the algorithm to be to choose the lambda, not in a very empirical way, but more depending on the scenario.
Yeah, analyzing the data, the different data of the global.
Yes.
Yeah.
Then the work would be more shifting on the data distributions. So information between mutual information and so on.
Okay, thank you very much. Any other question? Okay. So, thank you very much.
Something to add that Nori is staying until next Wednesday, you're leaving Wednesday, right?
Yes.
So she's available today, Monday, Tuesday.
Okay. When you want.
She's here to interact.